Following on from differentiating trig functions, last lesson we're now going to look at integrating some basic trig functions, specifically functions involving sin x and cos x. There are also a number of standard integrals and derivatives that are given in the formula booklet, so we're going to have a look at how we can make use of that. First, I'd like you to have a look at the differentiation we did last lesson. We had a go at some of these. Have a look at them with a mind to the fact that integration is the reverse process of differentiation, to try and inform yourself about how we might be able to integrate functions involving sine and cos. Did you manage to work that one out? The integral of sine kx with respect to x is minus 1 over k cos kx plus c. The integral of cos kx with respect to x is 1 over k sine kx plus c. Well, if you think about differentiating, if we're differentiating sine of something, sine to cos. So it's not hard from that to see that cos would go to sine, and if we're multiplying by, when we're differentiating, we'll be dividing by that part of the compound angle when we integrate. It's the reverse process. Same logic is true here. Cos actually goes to minus sine, but minus cos goes to sine. So we can see here a very similar process. Here, sine differentiates to cos, cos differentiates to minus sine to minus cos, and minus cos to sine, and so on. So going clockwise, we're differentiating. Integrating is the opposite way. So you can see here that going anti-clockwise, sine goes to minus cos, cos goes to sine. And you can see those results up there. So to integrate sine 5x, well, sine goes to minus cos if we follow our circle anti-clockwise, and the 5 goes underneath, so doesn't it? So it becomes minus 1/5 cos, and the compound angle stays the same, 5x. There we are. Don't forget the plus c. We have the constant of integration, because we don't know what constants have disappeared when we've differentiated. Let's try another one. 7 sine 5x. Well, again, sine goes to minus cos, the angle stays the same, and the 5 goes underneath. So we get minus 7 over 5 cos 5x plus c. There are some pretty complicated looking trig functions that you're asked to integrate in Core 3, but they're not as bad as they look because they're in the formula booklet. It's important to note though that there are two places to look. The obvious one, we look at integrals and we get the results here, but we can also use the differentiation section the other way round. So obviously, being a reverse process, we can integrate by using the derivatives here in reverse. What about cot x then? Using the formula booklet, and then mod of sine x plus c. What about that nasty looking integral? There we are. That just integrates to a half cosec 2x plus c. Notice the angles staying the same, and here we're dividing by, hence the half here. minus 3 cot 3x goes to minus a third ln of mod of sine 3x plus c. At this stage we can't integrate sine squared x and cos squared x. In order to do that we need to use the double angle formula that we learn in core 4. Okay, well you're now equipped to deal with these sort of questions, so have a quick go at this matchup. If you're successful with it, then I think you're about ready for the lesson on integrating trig functions. Pause the presentation and have a go. And that's what you should have got. The next few lessons are going to look at some coordinate geometry, to do mostly with straight lines, with the equations of straight lines, gradients, and this first lesson on length of lines and midpoints, or lengths of line segments. It's important to make that distinction. We're talking about a line segment between 2 points as opposed to a line with an equation which goes on forever, which has infinite length. There are formulae for finding the midpoint and the length of a line segment, which we need to both know and also know how to apply. So to start with, we have 2 points here, A at -2, -2, and B at 1, 3. To find the midpoint, M, we need to average the endpoints. We can see that the x points we've got are -2 and 1. So if we add them together and average them, divide by 2, we get -1/2. So that gives us the x ordinate. To find the y ordinate, we look at the two y values, we add them together, find the mean, and we get 1/2. So the formula for the midpoint of AB, where that's the line AB, or the line segment, if we give general points here, so xy and xy, we'll call this xy coordinates x1 and y1, and then to make it distinct we'll call this point here x2, y2. So to find M, we add x1 and x2 and divide by 2, and we add y1 and y2 and divide by 2 to give us our coordinate pair. Okay, so the point M is easily found like that if we know the coordinates of each of the points, each of the endpoints. Okay, have a go yourselves. Pause the presentation and give it a try. So it was just applying the formula, so hopefully you were successful. You should have ended up with this coordinate pair here. If you weren't, if you struggled with it, then go back over it and make sure you know it, because you really do need to know this stuff so we can move on. So the length of a line joining 2 points. Well, we'll work with the same 2 points. And hopefully you'll recognise what's going on here. We've worked out this length here. We can see it's 3. We've worked out this length here, which we can see is 5. Using Pythagoras' theorem, the square root of the sum of the squares of the two smaller sides gives us this length here. or in other words, the sum of the squares of the two smaller sides gives the square of the hypotenuse, which is what AB is. To find out the length of AB, we then square root the result. So we've got the square root of 9 plus 25, which gives us root 34. We'll recognise this as being a surd from the work we've done in the previous couple of lessons. And there's not a lot we can do with that surd. There's no square numbers that are factors of 34, so we would leave it like that. So, in general terms, if we make our coordinates at A, x1, y1, and our coordinates at B, x2, y2, then to find the length, it's the difference in the x coordinates, x2 minus x1 for this length, and the difference in the y coordinates, y2 minus y1 for this length. Using Pythagoras' theorem, if we square them both and add them together, we get the hypotenuse squared, we get AB squared, and then square root to find AB. So for example, we're trying to find the length of the line joining the points 4, minus 3 to minus 1, 2. We put the difference in our y values and the difference in our x values into the formula. So x2 is minus 1, x1 is 4, so we put that in there. y2 is 2 and y1 is minus 3. Work it out and we get root 50. We can simplify 50. 25, which is 5 squared, goes into 50. It's 25 times 2, so we simplify that to 5 root 2. Okay, have a go at this. If you're successful with this and you were successful with the previous one, finding the midpoint, then you should be about ready to move on. So pause the presentation and have a go at working out the length of the line AB. So here's the solution. Hopefully you were successful. 16 goes into 32, so we can simplify that to 4 root 2. So to summarise, we have this equation to find the midpoint, this equation to find the length of a line.